The mass hanging on the end of this spring is in its rest or equilibrium position. In this equilibrium position, the downward force of gravity is balanced by the upward force of the spring. The force of gravity or weight is always the same. As the mass is pulled downward, the upward force of the spring becomes greater than the downward force of the mass. This causes a net upward force. When the mass passes through its equilibrium position, the two vectors cancel out, leaving no net force acting on the mass. The mass has stopped moving at the highest position of its motion. At this point, there is a net downward force. Recall Newton's second law, F equals ma. At this position, the mass experiences a net upward force, which results in acceleration upwards. As this is position with the greatest upward force, this is the point of maximum upward acceleration. When there is no net force on the mass, it has no acceleration. The velocity is at its maximum here. Here there is a net downward force and the mass is accelerated downward. The velocity is 0. This is simple harmonic motion. 1. The acceleration is always directed toward the rest position. 2. The acceleration increases as the mass moves away from the rest position. Hooke's law, F equals negative kx, describes the force exerted by a spring. The force is a restoring force. The negative sign indicates that the force is directed opposite the direction of motion. The spring constant is k, and the distance from the rest point is x. When the mass is at the lowest point in its oscillation cycle, two forces act on it, an upward force, F equals kx, and a downward force, F equals mg. The difference between the forces is the net force, kx minus mg. Here the spring force, kx, is greater than the gravitational force, mg. Here the net force is ma, and it causes upward acceleration. At the top position, the spring force, kx, is smaller than the gravitational force, mg. The difference is the force minus ma, which causes the mass to accelerate downward. If the spring is stretched 15 centimeters by a 45-gram mass, what is the spring constant K of the spring? A. 2.9 newtons per meter. B. 2.9 newtons. C. 2,900 newtons per meter. D. Correct. Please check that you have written your solution in a formal manner as shown. If you wish to receive full credit, your solution must show the concept F up equals F down, the steps you took in solving the problem, and the answer expressed with correct units and with the correct number of significant figures. The block moving back and forth has the following characteristics. Equilibrium point. Amplitude. Period. Maximum acceleration to the left. Maximum acceleration to the right. Zero velocity. Maximum velocity. At this point, the spring exerts the greatest push toward the right. At this point, there is no force acting on the mass. Recall that work is defined as the force exerted on an object times the distance that the object moves. The area under the line is the width times the height. In this case, the width is the distance moved and the height is the force exerted in moving it. You can see that the area is the work done on the block by the person pushing. The equation work equals force times distance is used when force is constant. What if the force varies with distance as it does in the next frame? Here's a graph of F versus X for the spring mass system. Notice that the amplitude to the left is shown as X sub A. The force is at its maximum at negative X sub A, and the force is 0 at the rest position. Imagine the block moved all the way to the left and then released. The spring pushes with a maximum force initially. This force drops to 0 at the origin. The area under the diagonal line is the work done by the spring on the block. Since the base of the triangle is x and its height is kx, the work done by the spring is equal to 1/2 times k times x squared. The areas of the individual columns fx times dx are added to give the total area, which is equal to the total work done by the spring in moving the block from its initial position, x initial, to its final position, x final. This is done mathematically by integrating force times displacement from x initial to x final, or minus k times x from x equals minus x sub m to x equals 0. We obtain the result that the work done by the spring is equal to 1/2 times k times x sub m squared. From the leftmost position, the force is positive to the right, and the motion is positive. As the block continues past the rest point, the force becomes negative, directed to the left, while the motion continues in the positive direction. Since x sub m equals a, the formula for work done by the spring becomes work equals 1/2 k times a squared, and as the block moves from x sub I equals negative a sub max to x sub f equals positive a sub max, the work adds up to 0. Suppose that k equals 52 newtons per meter, and that the block moves from x equals minus 5.0 centimeters to its unstretched or rest position. How much work is done by the spring? A. Correct. Check to make sure that you have shown a complete solution. Consider the block moving back and forth. The energy of the motion across the rest point is the kinetic energy, 1/2 mass times velocity squared. The energy at either end of its movement is the potential energy, 1/2 k times a squared. At any moment, the sum of the kinetic and potential energies equals a constant amount of energy. Conservation of energy means that the work done on a spring moving it from its rest point becomes potential energy at the new position of the block. This potential energy would then become kinetic energy if you released the block. How fast would a 2.0 kilogram block be moving at its greatest amplitude, A equals 1.2 meters, if you pushed it with a force of 12 newtons? A. 15 meters per second. B. 1.5 meters per second. C. 24 meters per second. D. None of these. Incorrect. Try again. Incorrect. Try again. Incorrect. Try again. Correct. At its maximum extension to either side of the rest point, the velocity is 0. How fast would a 2.0 kilogram block be moving at its equilibrium position if you pushed it a distance of 45 centimeters with a force of 12 newtons? A. 23 meters per second. B. 2.3 meters per second. C. 42 meters per second. D. I could use a hint. Conservation of energy means that if you do a certain amount of work, W equals F times D, then that work is converted first to potential energy, and then to kinetic energy. Correct. Check to see that your solution includes the concept that the work done by the spring equals the potential energy of the spring, which equals the change in kinetic energy, the algebraic equations used, the numbers substituted into the equations, and the correct answer expressed in proper units and number of significant figures. At any moment, the total energy in the spring block system is the sum of the kinetic and potential. If we substitute in the values for the kinetic and potential energy, this equation can be solved to find the velocity. The plus or minus sign in the bottom equation here indicates that the block could be moving in either direction. A 1.0 kilogram mass attached at one side to a spring with a force constant of 45 newtons per meter is oscillating back and forth. Find the total energy of the system if the amplitude of its motion is 5.0 centimeters. A. 24 newtons per meter. B. 5.6 times 10 to the minus 2 joules. C. Neither of these. Correct. Check your answer. Do the same problem as before, where a 1.0 kilogram mass attached at one side to a spring of force constant 45 newtons per meter is oscillating back and forth with an amplitude of 5.0 centimeters. Only this time, find the velocity at plus 2.5 centimeters from the rest position. A. 0.53 meters per second. B. 1.06 meters per second. C. 0.29 meters per second. D. Hint. Correct. Try again. Correct. Try again. Correct. Try again. Correct. Check your solution. In our previous discussion of simple harmonic motion, we demonstrated that the position, velocity, and acceleration of a harmonic oscillator can be described by the three following formulas. Position, x equals a times cosine omega t. Velocity v equals negative omega times a times sine omega t. Acceleration a equals negative omega squared times a times cosine omega t. Here a is the amplitude of the motion and omega its angular velocity. Omega is related to the motion's period t by the formula omega equals 2 pi over t. Comparing the expressions for the position x and the acceleration a, we see that for simple harmonic motion, we can express the acceleration as a function of the position, a equals minus omega squared x. Because the mass spring system exhibits simple harmonic motion, we can use the previous relation to describe the acceleration of the mass. Multiplying both sides of the equation by the mass m and applying Newton's law to the motion, we obtain a relation between the force applied to the mass and its displacement. Comparing this expression with Hooke's law, F equals minus k, the spring constant, times the displacement x, we obtain omega equals square root of k over m. Since the period is t equals 2 pi over omega, and the frequency is the inverse of the period, we can express the period and frequency of the mass spring system as t equals 2 pi times the square root of m over k, and F is 1 over 2 pi times the square root of k over m.